So yeah, I'm delighted to be here tonight, and I want to take up a thought that that Tim mentioned earlier, that we as a human mankind need urgently some ways to coordinate in order to tackle these coordination problems like global climate change or resource distribution, so that we as human mankind basically can survive this kind of century, basically. And in blockchain in itself, like Ella described earlier, can provide such an infrastructure where we can create governance tools upon it. And in order to build an infrastructure that can create in order to create an infrastructure that can scale at a global can scale at a level where we can coordinate human activities, we have to take some other approaches, and we've learned in the talks earlier that there are blockchains that currently are not scalable, so we need other approaches. And I want to talk in this. I want to give you some ideas in the talk how RChain takes up principles out of nature, how nature scales. So yeah, same disclaimer. All this kind of information are not meant to be trading advice. Just a few words about myself. I got involved into the blockchain space in 2010, mined a little bit, then didn't really get the concept behind it, forgot about that, and then 2013 heard about Bitcoin again, and well, you've mined some Bitcoins, but yeah, I was one of those unlucky guys who lost his private keys, but fortunately, I was there when Vitalik Buterin published his very first blog post about Ethereum. And it was one of those mind-blowing moments where you realize this is something that truly can change the world, how we can perceive it now. And I really got started into getting involved into the blockchain space. I helped a lot during the test phase of Ethereum. My original background is in physics, and then once I've got involved into the blockchain space, I changed my focus more towards computer science, learned a lot about game theory and mechanism design, and applied it on trying to analyze blockchain concepts. And yeah, lately I'm more involved into RChain because I think it can build an infrastructure in a secure and scalable way that we kind of need for these mission critical applications. And also I'm a member of the inblock.io team, and as I've said, we are a collective of blockchain enthusiasts. So I just want to take up the three key points which I think we've learned within the last years in the blockchain space. And there's the very first one is that proof of work, the consensus mechanism of Bitcoin, for example, or currently also Ethereum, is a pretty simple one. But it's certainly not sustainable, especially given that we are already heading towards a world where climate change is a pretty severe problem. So it is rather simple, and that's super good, because otherwise we might have not gotten the step upon trying to build blockchains in the first place. But we have to change the consensus mechanism to another one. And luckily, there is another way that is proof of stake, and we will hear about that later. Udo will talk about Casper. The second point is that writing Buggy smart contracts on blockchain, so these small programs that run on the blockchain infrastructure, is pretty easy. Writing correct ones is pretty hard. And certainly a lot of developers in the blockchain space had to learn a hard lesson. Think back of the DAO hack or the parity multisig hack, where millions of funds get lost because the smart contract wasn't developed in a proper manner. So we need some kind of other tools to write those programs on blockchains. And the third point is the small cute kitties here, that no blockchain currently scales. And if anyone says otherwise, well, I guess he's lying. And CryptoKitty is one of the first applications on the Ethereum blockchain, which basically showed us once more that we aren't there yet, and that these platforms are not ready for mass adoption yet. So, what does RChain do differently? So, as David already pointed out, RChain tries to build an infrastructure where we can build applications upon in a secure, sustainable, and scalable manner. And David also talked about those approaches, how that's done. So it's a pretty scientific, mathematical approach. We talk a lot about category theory, linear logic, or computational calculus. And also correct by construction is a very important approach there. So let's take a look at nature. How does nature scale? And if you take a deep look into our body, if we zoom in, we end up at a scale where there are some atoms, and those atoms form bigger structures, molecules themselves organize to cells. They form bigger structure, and then this goes on until we get some kind of an organism. And we can see one principle within this context, and that is that in our body, smaller, more complex structures are built of smaller ones, and they themselves behave as one entity. And interestingly, it doesn't stop at the human being level. So it is just one organism. We as humans form local communities, and society itself can be seen as a larger structure that basically is also kind of can be seen as one organism. So the one very first principle we can observe in nature is compositionality. So that smaller stuff create more complex structures. Another example are ants. Ants are awesome. They form colonies, and basically they pass messages by each other by using pheromones, and they communicate in an indirectly manner, but through the passing through these pheromones, they pass messages, and so they coordinate and they achieve them then. that is cool, and this is another principle that in nature, also in our body, they're for example hormones, and they regulate all those body interactions, and this is another principle that that through message passing we coordinate and accomplish things, whatever that means. And if we go back to the other example, we can see another point, the third one. There's cells in your heart, and those interactions are mostly independent from those interactions of the cells in your toe, for example. And there is no need that everything needs to be that they synchronize in a way for every interactions. So they happen at the same time, and there is no need to sequentialize or to order all those transactions or whatever. And this notion is that this is concurrency, the principle I'm talking about. And we can observe this principle also in the financial system. The financial system also only scales because there is no need to order every transactions. If I pay, if I buy coffee here in a cafe, then there is no need to sequentialize and to order the transaction with a transaction that's going on at the same time when a taxi driver, cab driver is paid in China. So we have those three principles. There are compositionality, that bigger structures and more complex structures are built of smaller stuff. There is concurrency, that interactions happen at the same time, and most interactions happen independently, and there is no need to sequentialize them. And there's coordination through message passing. So often those terms concurrency and parallelism get mixed up, so I just want to give a little example on what parallelism means. Think of a highway where you have 4 instead of 2 lanes, and for parallelism it wouldn't be allowed to cross lanes. But what does this accomplish? Instead of having 2 lanes, having 4 lanes increases performance and throughput. On the other hand, concurrency is when you have, for example, 4 lanes, but lane crossing is allowed, but in order to do so, you have to use blinkers, or you have to signal the other car to make some space so that you can cross the lane, and yeah. And concurrency is more about resource management instead of just increasing the throughput. And yeah, it also avoids race conditions. So it is kind of whenever there is a congestion of resources, concurrency finds a way to avoid that in a way. So David talked about the 3 generations of blockchains, and Bitcoin was the first one. It was basically a distributed ledger where participants find consensus about the account balances, basically. And Ethereum came around, and Ethereum provided a way to find consensus about the state of a virtual machine. And now the question was, what kind of virtual machine should we use? And Ethereum decided to use the EVM, which is basically a Turing machine, or to be precise, a Von Neumann machine. And the EVM works sequentially. So there is a need within this computation model of the Ethereum virtual machine to sequentialize every transaction. And now one can think of, well, maybe we can find another computational model, another way to build a virtual machine that fits better our domain of blockchains. And Greg Meredith, the thought leader of the RChain project, came up with some requirements for that. And he calls them the 4 C's, and then there are 2 other ones. And 2 out of the 4 C's we already know. That is the compositionality, and the other one is the concurrency. And then there is completeness. Completeness means that you just want to have a way to write arbitrary programs, every program you can think of, and complete in a way of Turing complete, you might know that. And complexity means that you need a notion of try to calculate the execution costs. So you need a way to figure out how much resources are needed in order to execute a program. And then there's type theory, which is important if you just want to use, for example, formal methods and want to find proof that you want to have guarantees about your program. And then there is metaprogramming, which is a way that programs, for example, can write programs. Let's think of, basically it's that. And if you go through the list of requirements and compare it with some known computation models, for example, the Turing machine, so the EVM, the Ethereum virtual machine is basically a Turing machine. And you can just try to compare with the list. You immediately will see, okay, completeness, yes, it is Turing complete. It is not compositional. You can't whack 2 Turing machines together and get a third one within the context of a Turing machine. It's also not concurrent. And that's one of the major problems with the Ethereum virtual machine, because it processes everything sequentially. And also the other ones are not that good. Then you can look around and see whether there are other computational models that might fit better the domain of blockchains. There, for example, the lambda calculus, which is the foundation for every functional programming languages. It is for sure compositional. That's one of the major selling points of functional programming languages, but it's not concurrent. There's a theorem that basically every functional programming language process sequentially. So we see also that doesn't work out. Then there are some others, Padronets. And it turns out that the pi calculus, the process calculus, almost fits all of these criteria. The one that's missing is the metaprogramming, so the notion of the program can write programs. And it turns out that it is possible to add that feature, and the row calculus was born and invented by Greg Meredith. So just a short history of computational calculi. Robin Milner came up with this idea in the 1990s to create a new computational model that describes better the way basically computers processed at that time already. So it was that there were many computers working together to solve one problem, and each of those computers processed a small piece of the information and passed it through towards the next computer. And so it tried to create a computational model that takes this message passing in. And it turns out that not only is this possible, but it's everything you need to do the computation. The message passing is all you need. The computation lies within the message passing in itself, which is quite amazing. But it's also something we observed, or we learned, that nature basically does the same thing. when you have molecules that are passing hormones in order to, organs that basically send out hormones and messengers in order to coordinate and accomplish things in your body. And yeah, Greg Meredith, the thought leader of RChain, came then and invented this reflective higher order process calculus in the mid-2000s. So I just want to give you a very easy way to learn about the row calculus. So in the row calculus, there is a notion of do nothing. That's very easy. We love that. There is a notion of to listen, for example, with your ears, and for something specifically, and then you do something. There is a way to describe, for example, call a telephone number, call a person, and type in your number, and tell them something. There's also the notion within this computational model to do multiple things at the same time, so do two things in parallel, multitasking basically. And then there is, for example, a notion to look something up. For example, get the phone to a given telephone number. Or for example, look up what's written in a book at a certain page. And this is basically the more formal way to describe it. Yeah, so let's go through it. It's absolutely the same. We have P and Q are processes, and all these different kind of lines denotes here a different kind of option. So there's the option that the process do nothing. The process does nothing. Or basically it terminates. Then there's the way to, this is basically called the for comprehension. To listen on a channel Y, listen for a pattern X, and if you receive that, then do something. And do something is again a process. And there's the notion of send a process on a channel X. There is a possibility to run two programs in parallel. And there is the notion of dereferencing, where you basically given a name, which is X, basically evaluate that and get a process. And also for names, there is the possibility to get the process by quoting, so putting an at before that. And basically, you see there is a symmetry. There's a symmetry between names. You can turn names into processes, and you can turn processes into names. Yeah, David already talked about the programming language Rolang before. So just a few words. It is basically very similar to the row calculus I've just described. It's syntactically very, very close. There will be, for Mercury release, there will be spatial types, which is a type system that gives you an impression about the structure of the program. Later on, there will be behavioral types where you can reason about the behavior of a program, and that's where it really gets interesting, because it makes much more easy to reason about what does actually my program. And if you think about that, the programmer has an intention in mind when he just wants to write a program, and in some cases the developer writes a specification, and then later on he does he or she does the implementation. But on every step, there can go something wrong, and the behavioral type system gives you another guarantee or another check to see later on when you've implemented your program. Does this fit my intention? Can I see within the type system that is actually what I had in mind in the first place? It also provides very good opportunities to basically use formal methods in order to come up with guarantees that your program does what you specified. And an example for this could be, for example, think of GitHub, where you currently can just basically either you've given a hint by someone to use this library on GitHub, or you search by text, but what are you searching for, text snippet or whatever? It's quite difficult to find other libraries you want to use if you don't know where to find them or how do they look like or whatever. So given a behavioral type system, you could search for the behavior of a library or program, and it makes it much easier to reuse other programs. And that is also a notion of scalability, that you don't reinvent the wheel again and again.